left off here talking about the NSA's cryptic tips about quantum computing. And all right, so here's what they say. A sufficiently large quantum computer will be able to break all the current public key algorithms, and they think that the longer versions are all right for a while, like AES 256 and SHA 384. By the way, I should mention, Linux, like your Corley, and the Macintosh have been using SHA-512 with 5,000 rounds to hash their password for years. They really always use the best of everything, and that's probably part of why they cost so much. Anyway, so why the Macs cost so much. So there's what's recommended now: 384 bits for elliptic curves, 3,072 bits for RSA, and so on. And that is their current guess at something that will survive the early days of quantum computing, but they're currently searching for a whole new generation of algorithms that will be quantum resistant, whatever that means. And it's going to be hard to really be sure about that until we really have these quantum computers so we can see what they can really do. But the point of quantum computers, he was asking, a quantum computer is like condensing a gas. If you have a gas and you cool it down and it condenses to a liquid and falls to the bottom of the vessel, it changes from a state of high entropy to low entropy. And so that's what quantum computers are like. You have these qubits that are mixed, they're either 0 or 1, and they have a probabilistic mixture of the two, and then you cool the temperatures so they all stabilize into the solution. But the point is, instead of going through some algorithm where you go step by step, doing mathematics on bits to get to the end, you start in a chaotic state, and as you cool it, all the individual qubits explore cases and find their way to the bottom. They get to the answer without passing through a set of steps to get there. That's why they can solve apparently unsolvable problems, because every particle acts like its own processor, exploring all its options. Anyway, it's sort of like magic, but like anything else, they've really got it working in a huge industrial setting with cryogenic temperatures and expensive equipment, and it'll take decades to boil it down to something we can afford to buy and carry around. Anyway, so that's the game. Then there's another one, because certain prime numbers are used all over and over again. A lot of people believe that the NSA can crack a whole bunch of HTTPS because, again, the things that should be random are not really random. And they're able to, so that was a game here. They claim that they can probably crack up to 20% of the world's HTTPS traffic. And this is why the NSA for years has been archiving all of the internet traffic in the world at a center in Utah. They're keeping all the packets that they can't open because as time goes on, they figure out how to open it later. And that was why when this came out, there was a big jump to TLS 1.2, which most of the internet is now using, that uses a different key for every connection. So that you have this property called forward secrecy, that if someone gets the key for one session, they can't decrypt future sessions with the same key, which used to be the case for almost all websites. So then there's a digital signature. This is the thing specified in the 1998 Digital Millennium Copyright Act to make it possible to do business over the internet. So what you do is you want to do a financial transaction, like a loan. So you have some kind of loan agreement that says, I will pay the bank this much money every month, or they can take my house. Now, this is not a secret. As a matter of fact, this is going to be a public record. What you need is to sign it. So you calculate a hash of this, like an MD5 hash or SHA-1 hash or something. Then you encrypt the hash with the private key of the sender, and you attach all three of these things and send it in a public record. There's nothing secret here, but this is the digital signature. And the way this works is anybody that wants to verify that document, they can take the document, calculate the hash, and see if it matches. And if it does, that means that this hash matches the document. Then they can decrypt this with the public key and see if it matches. And if it does, that proves that the document has not been altered since I signed it, or the hash would come out different. And it proves that I signed it because I had the private key, and nobody else has the private key. So this is what you want. This is what the point of signing with a pen on paper was supposed to do. It means that I cannot lie later and say I didn't sign this. There is proof that I signed it, and it is really the same thing I signed. It hasn't been altered. That's what you want. And with this system, with public key encryption, you can now do financial transactions over the internet without having any trusted third party or any physical piece of paper with a pen. Well, there is, in this part, there's no trusted third party, except if you think about where you got the public key, which we're going to get, there's an issue there. Anyway, that's the digital signature standard, and this uses RSA algorithm and SHA algorithms to do it. Pretty good privacy is what Phil Zimmerman, go ahead.
Question on Adobe Signature?
Yeah.
Do they do it the same way?
I've used it, and I think they do. They claim they do. I haven't gone into technical details, but Adobe supposedly is doing the same thing, yeah. And the thing that kind of troubles me about it, though, is the things like the Adobe Signature are using a transient key. You don't actually keep the private key. So I don't really understand how they can be sure later that you signed it. The key handling is the bad part of all this. Where do you have your private key, and how do you make sure that you don't lose it, and how do you make sure nobody else copied it? This is a huge problem. And the math all assuming you have your private key and you don't lose it and you don't let anyone steal it, but they don't tell you how to do that, and in fact there isn't much of a good way to do that. So Phil Zimmerman invented pretty good privacy to encrypt email, and I tried to do the same thing at the same time, or maybe I was earlier, but I was using an 8-bit processor, and I couldn't figure out how to make this work on an 8-bit processor, and I saved myself decades of grief, because when he did make this system and put it on the internet, the US government accused him of selling weapons to our adversaries and being a traitor, and he had to spend about 10 years fighting the government that wanted to lock him up for providing tools to our enemies that they could use to make encryption we couldn't crack. Every government seems to rely upon strange mythological structures, but the US's mythological structure is our enemies, like North Korea and Russia and China, they don't know how to do math. They don't have any mathematicians over there. So even though the mathematical papers are already public showing how to do this, they won't be able to figure out how to write the software if you don't write it and put it on the internet. And this is a very strange position to take. You know, in Russia, they have chess players, and they're heroes the way our football players are heroes. You know, I think they're way ahead of us on math. I think the Chinese are doing pretty well on math, too. I don't know who they think they're fooling. But anyway, the government has a long history of trying to conceal math as if you could keep math a secret, which is pretty illogical. Anyway, PGP is a free public key encryption program. There's a pay version and a free version. It uses certificates, but it doesn't use a centralized authority to sign them. People sign each other's certificates. Anyway, it can support a lot of algorithms, and you can choose stronger or weaker ones. There's another thing called S-MIME, which is used to encrypt the attachments to email, and it uses public keys and certificates. Another one called Privacy Enhanced Mail that can use it. Anyway, so that's symmetric cryptography and asymmetric cryptography. The third kind of encryption that matters to us is hashing. These are the only three things. There's a world of mathematics with thousands of cool things, but there's only three that really matter to us on the internet that were used, and that's secure symmetric algorithms, asymmetric cryptography, and hashing. The point of hashing is to put a fingerprint on a message. So I can take a file and have some kind of hash, and that's like a fingerprint. So if I make a copy of the file and calculate the hash, and the hash is the same, that means the whole file is identical. That is the goal. No hashing can ever be perfect because the hash is smaller than the file, so there are in principle more files than there are hashes. So there are in principle two files somewhere that hash to the same hash value. But you want it to be so rare that you can never find those, and therefore you can trust the hash. That's called a collision. If there are two files that hash to the same value that are different, then the hash no longer is an effective fingerprint. It doesn't prove what file you've got. And a hashing algorithm with collisions is considered broken, and people say you should quit using it. MD5 was the first really popular hash algorithm. Microsoft designed their Windows password hashing system before MD5 was written, and they used its predecessor, MD4, that's even weaker. And MD5 was never approved by the government for any purpose. It was broken before the government got in the business of approving cryptographic algorithms, but it is very commonly used, but it has known collisions. And my previous class before this, when I used to teach at 120, I had students play with a hash collision. You can generate them, you can make files that have identical MD5 hashes, but different contents. SHA-1 had no known collisions until one came out about 2 months ago from Google. Google researchers actually made two files that hash to the same SHA-1 that are different files. It was a big deal. People have been warning for years that SHA-1 is falling. SHA-1 should have been good for 1,000 years, but it turned out to have a mathematical weakness that made it easier to find collisions than it should have been because it wasn't perfect at scrambling the bits. And now this did indeed happen. It was widely expected to happen by the end of last year, but it happened, I think, about a month ago that Google found a collision in SHA-1. And so on the internet for a while, you'd see the browsers are now no longer supporting SHA-1 based certificates. All right, And that's the game. Many people saw this coming, that a SHA-1 collision would be possible in 2015 and early 2017. When I wrote these slides in January, updating them, it hadn't been found, but it was found about a month ago by Google, the first known SHA-1 collision. So SHA-1 is now considered unsafe, although, like WPA, TKIP, the fact that one powerful company can break it doesn't mean an average hacker can get in, but it does mean some people can get in, and as the years pass, more and more people will get in, so you really better not trust it anymore. Here's the schedule of all the browsers. Various browsers have started, in 2014, Chrome started showing a warning, and now it goes for every browser has been gradually increasing their warnings and blocking certificates that are based on SHA-1. And by now, they're probably all going to quit accepting SHA-1-based certificates because you can't really trust them, because that fingerprint does not mean the file has not been altered anymore. Here's ccsf.edu test. This is kind of a fun test. You can test your certificate at Qualys or anybody's certificate. I did a test testing the top 100 banks to see how good they were and the top 100 colleges. And here's what happened in 2014. See, there was a few A's and a few F's in colleges. And then I think here's the banks. You know, I went and did this every now and then to see how they're doing. Banks are better. There was only one F. Anyway, this is a fun test to run. You can learn a lot about HTTPS certificates from it. There are a lot of things to go wrong. And as in most things in security, what it really tells you is how old the certificate is. Anybody that hasn't updated their stuff for a couple of years, there are known defects in the algorithms they're using. So digital signatures have the hash value, which assures integrity, so you can't change anything about the document. And it uses asymmetric encryption, so you have authenticity, you know who signed it, and you have non-repudiation, they cannot deny later that they signed it. And so that's what you need for business transactions. So here's a summary of it all. Here are the symmetric algorithms that are important. You've got DES, which was the official government standard until the end of the 90s. And now it's considered unsafe to use. Triple DES was the simple patch on it, and that seems fine to use. AES is fine to use for the moment until we get quantum computing. And these are other ones, idea of Blowfish and RC5. They're all fine to use if you choose a reasonably long key. All right, here's the public key encryptions. Diffie-Hellman is key exchange, not encryption. RSA is the prime number system, considered secure, and so is ECC and LGMAL. They're all considered secure at the moment, but they're all of these are likely to be greatly affected by quantum computing, so in the next decade or so, changes in the recommendations can be expected, as all current versions of this will fall, and we'll have to go to some later versions to cope with quantum computers. Then there's hashing algorithms. There was MD2 and MD4 and MD5, ones that MD5 became very popular, but it has known collisions. Now SHA-1 has known collisions, and SHA-1 was considered the giant step up from MD5, and everyone switched to it, and now we're all trying to rush up to SHA-2. And there is a SHA-3 that was approved a couple of years ago we can go to if someone cracks SHA-2. But right now, almost everybody's using MD5 and SHA-1, and they're being pressured to knock off the SHA-1 by the browser manufacturers. All right, so I got a few more iClicker questions, and then we'll talk about the real dirt, which is not the math. The math is fine, it's the human element that leads to the real security disasters. All right, so if Alice wants to send a private message to Bob using asymmetric cryptography, what key does she use to send a message, to encrypt the message? Yep, this is the heart of the whole thing. You will see this on every security exam. This is the heart of the whole chapter. I'll wait till 45.
We get an extra minute.
I'll wait. What do you see? Now, most people are in. Now 45 should be enough. Pick one. A lot of people usually get it wrong the first time. You'll get used to it. All right. So the right answer is Bob's public key. Let's see how many I've got here. Right. That's not as bad as I sometimes see, but I don't expect. All right, let's talk about this. This is why it is really strange. Public key cryptography means you can receive secrets. If you want to send Bob a secret, you have to send a message encrypted with Bob's public key so Bob can open it with Bob's private key. Alice's keys have nothing to do with it. That's the weird thing about public key encryption. Public key encryption does not let you send secrets to anybody. It only lets you receive secrets. So if anybody wants to send a message to Bob, they have to use Bob's keys, and it doesn't matter who they are. That's what takes a little getting used to. Yeah?
Isn't the public key the same for both Alice and Bob?
No, everyone has to have a different private key and a different public key. If they had the same public key, they could read each other's messages, and that's forbidden. By the way, there was a Toronto-based researcher that went through the internet and saw how many people had the same public keys, and he found that 1 in 1,000 of all the companies on the internet have duplicate public keys because they're using faulty random number generators, which is really bad because the whole system depends on all the public keys being different because you want to send the message and you want to make sure no one except the intended recipient can read it. And if somebody else had the same public key, they could read that. So everybody should have a different public key and a different private key. But anyway, that's important. That's why it's a little bit backwards thinking. You got to think about receiving messages, not sending messages, to understand public key cryptography. Let's try a couple more of these. Yeah. It is. It does. So I'm not surprised that a lot of people get this wrong, but you want to practice until you can answer that question. That question is at the heart of a whole bunch of cryptography questions you'll see. Just like if you take Cisco, 1/4 of the test is understanding subnetting. What network are you on? That turns out to be the one concept that underlies 25% of all the tests, and this is the one concept that underlies all comprehension of public key cryptography. All right, let's try another. Alice wants to sign a contract. What key does she use? That's right. And when you sign a contract, you're signing it for the whole world. Anybody can look at the public record and see your signature and tell that you signed it. It's not directed at anybody. I'll quit at 35. Now you sign it with your private key, and anybody that wants, and see, this is why, by the way, you're not alone. Your private key is the only thing that proves who you are. And by the way, I should mention, there's a story, my friend Doug came through yesterday. He told me, when this system first became common, the FBI all set up public key encryption, and there were FBI agents that put it on their business card, and they had the public key for public information and the private key for private information. They put them both on their business card, which is totally wrong, but it is very common that people don't understand this and do it wrong. I'd say cryptography is done wrong far more often than it's done right. It can be very powerful, but it's very easy to get confused and make a fatal flaw like handing out the private key that we were supposed to keep secret. So if you want to sign it, you sign it with your private key. If anybody wants to verify the signature, they can verify that with your public key. So we'll keep going. Let's try some more of these. All right. What process uses no key at all? Good. All right, I'll quit at 30. All right, and that's hashing. Hashing is just putting a fingerprint on a file. There's no secret, there's no message, it's just a mark you put on the file, and if you cache it again, you get exactly the same answer. There's no key. All right. Yeah.
So the reading is about hash and text.
Yeah.
And if hashing all it does is basically just confirm something.
That's
why
right.
Why would you want to hack that?
You hash things just so you can make sure they've not been changed. For example, if you send packets over a network, Ethernet uses CRC32 to make sure that when it goes to the other end of the wire, it's still intact, because networks do drop bits. And on the internet, you're worried because people maliciously alter messages to add viruses to downloaded files and things like that.
But why would you want to attack a hash?
Oh, for that reason. You attack a hash so you can, for example, this happened to Mint. Mint had someone hacked into their server, and they changed the copies of Mint, so people that downloaded Mint Linux were installing Trojan software. And if what they did in that case, people weren't verifying the hashes, so it had the wrong hash and no one noticed. But if you wanted to infect a router and add viruses to all the files that go through, you might want to carefully add viruses so that the hashes stayed the same, so you don't get caught. That's all. I mean, if you can crack a hash, then you can forge things, just like forging a fingerprint. Then even if people are verifying it, they'll still be fooled. And a lot of automatic signatures check signatures, digital signatures. And another one is when I connect to Google, right? I get a Google certificate. That it ultimately comes down to a hash value to verify it. So if you could crack the hash, then you could make a fake Google certificate that my browser would accept. And people at DEF CON did that about 6 years ago because the main certificate authority, VeriSign, was using MD5 for the hashing algorithm until like 5 years ago. So people at DEF CON made a fake certificate authority, and they could sign fake certificates and they would believe it because they had the same MD5. So if you can crack it, then you can impersonate people even through the cryptographic signatures. So now here's the problem. There's this public key infrastructure. See, a lot of this stuff relies on you knowing somebody's public key. But how do you know somebody's public key? Where does it come from? Well, it turns out there's a system to deliver the public keys, and this is it. This is a system of servers that hands them out. And so here's the plan. If I want to know whether I'm talking to Google, I get a certificate that comes down, and it will tell me this certificate has been verified, it came from Google, it verifies that you're talking to Google, and you can trust it because it came from Thought, and Thought is a trusted certificate authority, and you can tell that it hasn't been modified because at the bottom it has these hashes. It has a SHA-1 and an MD5 hash. So that's how you can verify that this certificate has not been altered. So if somebody could crack SHA-1 or MD5, they could make another certificate with those same values, and my browser would not know the difference, and they would believe that I was talking to Google when I wasn't. So that's what all the mathematical side tries to prevent. So these certificates come from a certificate authority, and there are about 100 of them. They are built into your browser. These are companies that are trusted to hand out certificates and to verify them. So you have to buy a certificate. It's only good for a certain period of time. After that date, it expires, and you can then buy a new certificate or extend the old one by paying again. If you lose the private key, or you get hacked or something, and you think that you can no longer trust a certificate, you can revoke it. It's like, say, I'm going out of business, don't trust it anymore. Then they'll add it to this revocation list, and browsers should not accept it, although we'll talk more about that later. You can also cancel certificates, revoke them permanently, or suspend them for temporary reasons. This certificate revocation list is online, and it tells your browser which certificates should not be trusted, even though they came from a trusted provider and are in their valid date period. Now, HTTPS strict transport security is one of the new features where you put a header field in the HTTP response from a server, and it tells the browser that this should only be loaded over HTTPS. This is a very good thing, so you only load it over a trusted feature. And here's how it looks. Facebook has this now. If you load the Facebook page and you look in the Chrome developer tools, you'll see strict transport security down here in the header. So Facebook now tells you it should only be loaded over HTTPS. Don't load it over HTTP anymore. So modern browsers will not make that mistake. The problem is, there's many problems. One of them is you got to back up your keys. Your private keys have to be backed up and saved. If Facebook were to lose their private key, then they couldn't open any of the messages they're getting from everybody using that certificate. Your certificate authority typically has a backup of the keys, so if people can hack in to your certificate authority, they can steal them all, and that has happened. The worst problem is the root certificate authorities themselves. You don't control this list. The people that made your browser, in their wisdom, just chose to trust certain people, like Baltimore and the certificate authority of some foreign country in Spanish, and the government of China, and the government of the United Arab Emirates, and all sorts of people that you might really not trust that much are in this list. And if any one of them sign any certificate, your browser says, okay, I trust it. It's all or nothing. You trust anything these people say, like the word of God. You can make your own certificate authority server. It's very easy. In Windows, you just add Windows components, turn on certificate services, and then you just tell it what kind of hash algorithm you want to use and what key length you want to use. It's really not very demanding or anything. It's the kind of cryptography your browser does all the time. The only thing is, once you do that, you have a certificate authority, you can issue certificates, but no one's going to trust them because they're not in the trusted list in the browser. You can add them in a trusted list to your company laptops, and then your company laptops will believe it. Everyone else will get a warning message saying this certificate is not from a trusted certificate authority. So there are attacks. You can just sniff. Port scanning, you send a little bit of traffic in, but you can just sniff traffic. That's one attack. An active attack is where you send in crafted plain text to try to get it attacked. The best encryption most experts agree the safest procedure is to make the algorithm public so everybody knows and it can be tested, and all your secrecy is in the security of the key. The military does both. They make the algorithm secret and they make the key secret. In general, in the commercial world, if anybody will not tell you what algorithm you're using, you should not use their product. Because time and time again, I do a lot of this. If you look into what they're doing, it's incredibly, blindingly stupid. If they won't tell you, it's because they made it up themselves. And there's a reason why the smartest mathematicians in the world write these things. The thing you think up yourself in the shower that seems so brilliant, I'll move every letter 3 to the left and then flip every bit. No one will break that. This stuff is trivial to break. If they aren't using a standard, well-known algorithm, you can be very confident that they are doing something stupid, and you don't want to trust them. Anyway, this is for hash collisions. This is just a fact that if you will ask, if I make a bunch of random files and hash them, you will find a collision when you make enough files up to the square root of the size of the hash. So if you have 365 birthdays in a year and we ask people in the room what your birthday is, by the time you have 23 people in the room, you have a 50% chance that you'll have a birthday collision, because it's not 23 chances in 365, it's the number of pairs of 23 people. And there's 23 times 22 over 2 pairs of people. I might match him, I might match you, you might match him. There's actually a lot of pairs. So this means if you have a 128-bit hash, like MD5, if you do 2 to the 64 files, you'll find a collision. It's the square root of the hash. And that's the game, 1.2 times the square root of n. So SHA-1 should have been fine. SHA-1 has a 160-bit key, so theoretically it should have taken 2 to the 80 calculations to crack it. And as we showed earlier, no one can even do 2 to the 72 calculations. That will take 1,000 years. So if SHA-1, if the algorithm had been perfect, SHA-1 would not be cracked. The reason it's cracked is because they found a way to make it faster. They found a way to shortcut finding those collisions. Anyway, so there are ciphertext-only attacks where all you can do is observe encrypted traffic going by, and you can't even send in data. There's known plain text, where you can send in text under your control and it will be encrypted. That's more powerful. And then there's chosen plain text, where you carefully choose plain text to pump out the information you want, and that's what these padding oracle attacks are. You carefully send something that doesn't quite fit into the block size, so they have to fill this one with padding, which I can guess, and now I can get information about the key. Anyway, there are various ways to do it. The brute force attack is the one that will always work. If your algorithm is perfect, in the sense that there's no shortcut, then you just have to try every possible key. That's the brute force attack. This is the best you can do. Nothing can defeat a brute force attack. If you have, this is your goal. If you design a cryptographic algorithm, you want it to be so strong that the only attack is the brute force attack. And then people just have to have enough time, and then you make the key long enough so that time is ridiculous, like 1,000,000 years, and that's what you call a secure algorithm. A man-in-the-middle attack is another dangerous one. Suppose you're in the middle. If I want to talk to someone, I'm the victim, I'm talking to, say, Google, I want to send up my password, I'll sit in the middle. This guy will say, I want to go to Google. I say, okay, I'll go to Google, fetch the page, hand it out to you. Now, Google will send you a certificate. I'll send you a different certificate with my key. You encrypt it with my key. I read it, re-encrypt it with your key. You get in your account, and nobody knows this has happened. And virtual private networks are in general vulnerable to this. SSH is vulnerable to this for sending commands up. This is a huge problem. HTTPS is not vulnerable to this. That's why you have a trusted third party. So if I sit in the middle between you and Google, and you ask for a certificate, and Google sends it to me, and then I send you a fake certificate, before your browser accepts it, it's going to ask a trusted third party. That has to be one of those 100 trusted third parties, like VeriSign. Is this really a genuine certificate? And if I was able to crack the hash function and forge a certificate to pass the test, which is what happened 5 years ago, then I would fool you. But if they're using a modern routine like SHA-2 here, and I can't crack that, then this third party will tell you not to trust that certificate, and you'll get a warning box saying this certificate is not from a trusted authority, and you have an opportunity to save yourself. In practice, 99% of end users will just close that box and go on because they don't understand what it means. So that's an issue, but the browser does detect the problem. Anyway, then there's downgrade. This is another one we were talking about. We were talking about domain controllers during the break. this got us in big trouble. Because the US government tried to pretend they could keep cryptography an American secret, they forced all systems shipped out of the country to have export-grade cryptography, which was much weaker stuff that we could easily crack. And this meant that all servers that wanted to serve pages to products to foreign markets had to have weak keys installed on the server. So all you had to do is tell it, I'm sorry, I'm a server in China. I'm a Windows 98 machine in China. I can only speak 40-bit encryption. And the server would do that. So that's called a downgrade attack, where you pretend that I'm a really old box. You better talk really old encryption to me. And that's pretty deadly. It's a big issue. This is why the right answer is to configure your server only to use modern secure ciphers and not let people using old insecure browsers use your product. But that's only practical when the US government finally knocked off limiting the export of encryption. This is why the cryptographers of the world keep fighting the government on this. If you try to make weak encryption used widely, you're poisoning the well. So now we can't do business without our secrets leaking all over the place. The only secure system is for everybody to use secure encryption. So you can use it all the time and refuse to use weak stuff and still reach your customers. Dictionary attack is a variation on the brute force attack, where instead of trying all possible passwords or keys, you try the ones that you think are more likely to be used, like the ones from a stolen database of passwords. And this turns out to be extremely effective in the modern world, while passwords are almost useless. As you've done in the projects here, you can do 100 million guesses easily to crack a Windows password hash. So unless you can choose a password that is not in the 100 million top passwords, people can pretty easily get in. So if you use a password manager and your password is actually like 20 random letters, that's pretty good. But most people don't. They just use the name of their dog and their license plate and their phone number everywhere, and that's why people get hacked all the bloody time. A replay attack is where you record packets and replay them. This is what happens on Microsoft Windows domains. You can use a pass-to-hash attack. You can take the network traffic from one authentication and just replay it for the next authentication to get into a different server on a Windows domain. It is a huge problem. Microsoft has responded by making it harder and harder to get that traffic off the network and harder to find it on hard drives in their various versions. Firesheep did this until recently. Almost every online service did not use HTTPS all the time. They used it only during the login, and after that they used HTTP and sent a cookie unencrypted, which identified you, so you could easily snap the cookie off and replay it. And you did this in the projects too, just manually stealing a cookie from Wireshark. Services that want to prevent this, there are tricks. You can use a secure cookie, so the cookie itself only goes over secure connections, but what's much better and simpler is what Facebook and Twitter and I think even AOL now have done, is just be HTTPS all the time. So everything is always encrypted. That will stop people from being able to steal the cookies off the wire. That's a very good solution. So password cracking is technically illegal in the United States because of the Digital Millennium Copyright Act. Researchers do it all the time. This is part of what I was saying earlier. Essentially, all security research is illegal, so we rely upon the good grace of the authorities, who will not prosecute you, hopefully, if you have an obvious public presence and they can see that what you're doing is beneficial to the world. But it is an unfortunate situation that we all take some legal risk to be involved in this community. Anyway, you need the hashed password file, which you get from either SAM database in Windows or Shadow on Unix, and then you can just try a bunch of passwords to reproduce those hashes with any of these programs. I think we used Hashcat is a modern one. There are many, many versions of these password hashing programs. SSL strip is an awesome man-in-the-middle attack where you stand in the middle and you downgrade the thing to HTTP. And this worked until about 6 months ago when Chrome finally patched it. So if I try to serve Google and it's not HTTPS, Chrome will not fall for it. It'll say, I'm not talking to these guys. These aren't the real Google. The real Google is HTTPS. Your Chrome browser knows the top 1,000 sites, and it knows whether they should be secure or not. But other browsers like Firefox and Internet Explorer don't know, and they'll still be fooled by this attack. So I think I've still got this in the projects. Yeah?
Did you mention HSTS?
HSTS is a header you put on your page so that when people load the page, it tells you, you should only load it securely. So if your first contact with the server is not poisoned, then your browser learns to remember that this should always be loaded securely. So that's an automatic way to accomplish what Chrome does. So you can do that on your own server. You can put in a certificate, deliver it over HTTPS, and add the HSTS header. So anybody that comes in insecurely is told to come back securely. And that's pretty good. Yeah.
On your certificate, are you able to tell whether it's on a SHA-2 or SHA-1?
Yes, and it's just right there. You can see it in the properties, and your browser will now warn you if it's depending on SHA-1. It'll start popping up boxes and maybe even just blocking all access to it. There's a whole timetable there. If it's trusting SHA-1, it's highly recommended not to do that anymore. And the better browsers like Chrome will actually not let you use certificates that trust SHA-1 anymore. So some websites will go dark. It forces all the website owners to upgrade their stuff because more and more customers can't see them. And then there was wildcard certificates. This was kind of incredible. So if I have a domain like samsclass.info, here, let me just draw a few of these up here. If I have turn on the lights. All right. Yeah, if I have samsclass, let's make it evil.com. That's what Dan Kaminsky used. That's a good line. So if I own the domain, evil.com, and then I have a bunch of things, like I have games.evil.com, and mail.evil.com. I could put certificates on each one of those domains, but to save money, I might get a so-called wildcard certificate, which is star.evil.com. And this certificate will be accepted for all those websites, anything that fits that pattern. Now, this is fine, but unfortunately, until about 5 years ago when this came out at DEF CON, there was a problem. Browsers were written in C, and the servers that sold certificates were written in Pascal, a really old, Pascal. And in C, this thing is stored in the browser like this. You have 1 byte for every character, and then at the end, you have a 0 byte to terminate it. That's how C stores things. But the way Pascal stores things is it has a byte at the start, which is the length, and then the bytes, and no null terminator. So what it means is I could buy a certificate for this domain, star, then a null byte, 00.evil.com. The Pascal server will see this as a perfectly valid domain because a 0 is just a fine character as far as it's concerned. It will sell me the certificate, and then when your browser, written in C, tries to use it, it will say, does this domain match google.com? And all it will see is star and then a terminator, so it will only see the star, which is a wildcard, so the answer will be yes. So I can buy that certificate, and then I can sign any page with it, and every browser will say it's a valid certificate. It's bloody awesome. It was the abuse of a wildcard certificate independently discovered by Moxie Merlin-Spike and Dan Kaminsky and revealed at DEF CON. And they sold about 20 of those to various people so you could play with them for a while before they finally realized what happened and revoked them and updated their server. And this is a very common type of security problem where both products are working as intended. There is no bug, but when you connect 2 products written in different languages together, you create a disaster as they misunderstand each other's traffic. All right, so I got a few eye clickers about that stuff. And that's the end of this. And then I'll say a little bit about some private stuff that I can't put in this recording. All right, so which one is a list of invalid certificates? Well, I went by. In fact, I have a little more to say about it too. Yeah. I'll quit at 30. All right, that's the certificate revocation list. And this system is unfortunately extremely ineffective because what happens is many servers that serve these lists are so slow to respond that browsers give up without getting an answer and then just accept every certificate. So to respond from that, they're trying to move to other protocols, and the most effective one so far is, again, Google independently put it in Chrome. There aren't that many invalid certificates in the world, so Google just put them in the browser with the browser updates, so it already knows the serial numbers of every invalid certificate, which turns out to be much more effective than trying to connect to the certificate authority servers online dynamically every time you load a page. And it would be nice probably if that became the new standard, but right now it's one of the many non-standard features. In many ways, you're much safer if you use Chrome than if you use other browsers because Google puts in the new security features even before they can get them widely approved. Anyway, And Chrome is now the #1 browser. Not, I suppose, primarily because of their security, but that's a good byproduct. All right, which technique decrypts a message by trying all possible keys? In principle, nothing can ever stop this attack.
It just takes forever.
Well, the only thing that does stop it online, of course, is like locking you out after so many invalid guesses. But if someone can do it offline, then there's really nothing to stop them here, except that it just might take too long. I'll quit at 45. All right, that's 40. That is a brute force attack. The simplest attack, you just try every key. One of them has to work. There is, by the way, one crypto system that you cannot use a brute force attack on, and that's the one-time pad. The one-time pad uses a different key for every letter. So every letter gets moved randomly. So if you try all keys, you will generate all possible documents. So you'll generate things that you can read, but they aren't the message. That is the only cryptographic system I think that is completely unbreakable by any attack, even the brute force attack. But the problem with it is your keys have to be very long, longer than all the messages you're ever going to send, and you can only use each key once. So you have to somehow be able to deliver these big keys, so it's almost never used on computer networks. But that's been around for centuries. That's the perfect crypto system. But it makes the key distribution problem even worse, and so it's very rarely used. All right, which one defeats encryption by impersonating a server? All right. I'll quit at 30. All right, and that's man in the middle. You get in the middle and impersonate the server. And the only cure for this is either a trusted third party or a trusted side channel, like you put a secret key at each end before. Somehow you have to have some other information than the network traffic to to defeat a man in the middle attack. So let me see who got the most right, and then I'm going to stop the recording and show you a little bit of top secret stuff. Whenever this thing is closed. And let me first I'll stop the recording and then I'll see who won. So this, okay, 123, chapter 12B. All right,